Hello everyone, my name is Adil Ahmed. Today I'll be presenting Chancel, a system that enables efficient multi-client isolation under adversarial program. This is a joint work between Purdue University, Seoul National University, and KAIST. It's been done by me, Juhi Kim, Jebek Siu, Insik Shin, and my advisors Pedro Fonseca and Byung-Young Lee. So, modern cloud machines implement a lot of sensitive services that have access to a lot of confidential data. For example, we have private messaging services such as Signal that has access to our contact information and our messages. We have navigation systems that have access to our location. We have DNA testing services that have access to our actual DNA, and other services such as machine learning and intrusion detection systems are implemented on cloud machines. So as clients, what we really want is that when we send confidential data to a remote service, we should have the guarantee that our data will not be collected without our consent. Modern hardware features like Intel SGX are actually designed to secure remote data. Let's look into what exactly SGX does. So we have the normal program's address space, which is completely accessible to the operating system, meaning the operating system can extract whatever contents it wants from the program. SGX divides the program into two parts, the enclave and the non-enclave part. The enclave part is special because software access from the operating system and other privileged components is completely restricted. And the enclave memory is also encrypted on the main system memory itself. What that means is that if a malicious system administrator who has physical access to the system tries to extract contents from the machine, they won't be able to do so. So, using the protections of SGX, we can actually secure remote data from cloud machines. For example, Signal might use Intel SGX to secure its service. Therefore, the cloud provider cannot access Signal's service. As a result, when we send our messages through Signal, we know that our messages are at least safe from the cloud provider. However, SGX does not secure data from untrusted code. So in the last example, if Signal service is malicious, what Signal could do is they could stealthily collect client messages. Even if Signal operates a benign service, they might have written a program that has critical vulnerabilities that might allow hackers to exploit the program and collect client messages. Worst of all, as clients, we would be completely unaware that this theft is actually going on. Prior research in computer security has actually implemented a lot of ways to restrict untrusted code. One of the most promising ways is using techniques called software fault isolation. Conceptually, what software fault isolation does is it creates a brick wall around an untrusted piece of code that restricts the code's access to any outside attacker. Then we provide this piece of code with a very narrow interface to communicate with the outside world. And that narrow interface is completely controlled by trusted services. However, prior SFI techniques, including the very famous native client, is inefficient because it requires multiple processes. The reason it requires multiple processes is that it doesn't really implement in-process isolation. So when you're going to run multiple clients, what you have to do is that you cannot really serve those clients in the same process, because if you do that, you run the risk of one of those clients stealing the information from the other client. So what you have to do is you must use multiple processes. However, multiple processes consume a lot of memory. So for example, let's say you run multiple processes to serve every single client. Now you can't really efficiently or securely share memory between these processes. So what you must do is you must replicate the shared memory in each process. And consider that you have a very large database, you could end up using a significant amount of memory, because the memory must now be replicated across each process. So using a lot of memory is undesirable in all circumstances, but it is especially unacceptable when it comes to enclaves. The reason is that SGX enclaves have very limited memory, which is only 256 megabytes. So if you use more than 256 megabytes, the system will have a lot of expensive page faults, which reduce performance significantly. So we ran an experiment using a key value store with 8 different clients. We ran the key value store with native SGX and native client. Native client secures the 8 clients in 8 different processes. So as we see, with just a 64 megabytes of a key value store, the performance of native client is significantly worse than native SGX, and the reason is that native client incurs a lot of page faults because it replicates memory across the 8 different clients. So in our paper, we see that native client SFI can be up to 16 times slower than native SGX. And this is where Chancel comes in. Chancel implements an efficient multi-client SFI. Conceptually, what it does is it allows multiple clients to be served within the same process in isolated threads, and it allows those threads to securely access shared memory. As a result, it can significantly reduce the memory consumption of the program and ensure very good performance for enclave programs, as I'll explain towards the end of this video. But first, let's take a look at what exactly is the design of Chancel. So the first part of Chancel is an offline stage where the program developer must use Chancel's compiler to compile a binary that is compatible with Chancel. Bear in mind, this is completely automated. The next 3 phases are actually online. So first, Chancel will create an enclave into which it will install its runtime. Then Chancel will load the instrumented program binary after validation, and then it will securely bootstrap different clients into different threads of the enclave. Finally, Chancel will enforce multi-client SFI. So, as I mentioned, the first stage is to instrument the program using Chancel's compiler. For the sake of this talk, let's assume our instrumentation does only 2 things. First, it reserves the registers R14 and R15, so the compiler assumes that these registers are not available. Then, the compiler bounds the memory reads and writes of the program. It bounds the writes of the program relative to R14 and the reads relative to the reserved R14 or R15. So for example, if the instruction was to write at address X before, afterwards it would be, let's check if X is within the range of R14 plus a fixed thread size, and then you're allowed to write at X. Bear in mind, this is a simplification of the instrumentation, and please refer to the paper for actual details. So the second part is to create an enclave program and load the instrumented program into the enclave. So the first thing is Chancel will create an enclave in which Chancel's trusted runtime will be installed. Then Chancel's trusted runtime, which has a binary disassembler installed, will take a look at the instrumented program that is provided by the program developer. It will make sure that the program is actually instrumented using the disassembler. Thanks to this, Chancel can support proprietary code. We don't really need the source code of the service. We only need to make sure the service is instrumented, and we can do that by just using a disassembler. The third step of Chancel is to securely bootstrap multiple clients. So, multiple clients will first attest Chancel's enclave using SGX enclave remote attestation, and then they'll transmit their data through encrypted channels that they will create with Chancel's runtime after the attestation is successful, of course. So they'll send their data, and Chancel will store each client's data in a different enclave thread. The final step of Chancel is to enforce multi-client SFI. So how Chancel does it is that it uses those reserved registers R14 and R15. So when Alice runs, Chancel ensures that R14 points to the private region of Alice's thread, so that Alice's thread can only write within the same thread region. But at the same time, using R15, the thread can still read from the shared data. And then when Bob starts running, Chancel does the same. It updates the register R14 to now point to Bob's per thread region, allowing write only to the private thread region, but reads from the shared data. And this concludes Chancel's design. Now, what we want to learn is what exactly is the overhead of Chancel over native SGX, especially what is the overhead of Chancel's instrumentation over native SGX. So for that, we ran all applications in NBench, which is a popular CPU and memory benchmark that has been used to evaluate a lot of SGX systems. We find out that the maximum overhead of Chancel is 24.9% and the minimum overhead can be as low as 0.6%. The disparity in overhead is because some applications are more memory intensive, and more memory intensive applications tend to execute more Chancel compiler checks, because Chancel's compiler checks are mostly for memory access. Nevertheless, the bottom line is that despite the high security guarantees that Chancel provide, its overhead remains modest across a range of real-world programs and benchmarking applications. Please refer to the paper for more details about this. Next, what we want to see is what exactly is the benefit of Chancel over prior SFI schemes that use multiple processes, such as native client. So for that, we ran Shield Store, which is an optimized key value store for SGX, and we ran it using 8 different clients. So we ran the experiment with both native SGX, native client, and Chancel. Native SGX and Chancel were using multi-threading. Native SGX uses insecure multi-threading, whereas Chancel uses its secure multi-threading that is enforced using its special multi-client SFI. In contrast, native client implements 8 different processes, 1 process for every single client. The overhead of Chancel over native SGX was only between 1.1% to 8.4%. More importantly, the benefit of Chancel is significant. So as we saw before, native client performs really bad when it comes to, because it incurs a lot of page faults due to replication of data across different processes. In contrast, the page faults of native SGX and Chancel are almost the same, and so is the performance. As I mentioned before, the performance overhead is only between 1.1% and 8.4%. So in our paper, we show that across diverse real-world applications with a huge amount of data and a lot of threads, Chancel outperforms the state-of-the-art multi-process native client SFI by up to 21 times in real-world programs, and up to more than 50 times in our custom benchmarking experiments. Please refer to the paper for additional details about those experiments. So finally, I would like to provide you a summary and conclude this talk. So the first thing we learned today is that SGX does not secure remote data from untrusted code. So if you're sending your data to an untrusted service, there is always a chance that your confidential data might actually be stolen. Next, we learned that existing SFI techniques can secure remote data, but they are extremely inefficient when it comes to multi-client enclaves because they must replicate data across different processes. Finally, I presented the design of Chancel, which implements an efficient multi-client SFI that is up to 21 times faster than multi-process SFI schemes like native client in real-world scenarios. Thank you so much, and now I'll be taking questions.